and today I'll be explaining my CS231N Spring 2022 project, classifying dogs using PAWS, a project exploring how a semi-supervised image classifier performs on fine-grained classification tasks with sparsely labeled datasets. Modern-day machine learning requires lots of labeled data, but oftentimes it's challenging and/or expensive to obtain large amounts of human-labeled data. Therefore, how to learn with less labeled data is an important computer vision and machine learning research area. This application-based project is aimed at exploring how a semi-supervised method of learning by predicting view assignments with support samples, also known as PAWS, performs on fine-grained datasets, where classes are very similar, while also using sparsely labeled data to understand how well this methodology works for fine-grained classification tasks with very sparse labels. We work with three datasets in this project: CFAR10, the full ImageNet dataset, and the fine-grained ImageNet subset of 120 dog breeds. CFAR10 and the full ImageNet were used to baseline and pre-train PAWS, while the focus of the sparse labeled experiments were performed using the dogs dataset. As a part of the training methodology, data is augmented using color jitter, random cropping, and random horizontal flipping, similar to the SimClear approach. Predicting view assignments with support samples, or PAWS, extends the distance metric loss in self-supervised methods like BYOL and SWAB to the semi-supervised setting. Like the SimClear architecture, PAWS generates two different data augmentation views of a given unlabeled image, one being the anchor view, the other being the positive view. Both of these views are passed through an encoder network such as ResNet50 and then generate representations. Class predictions are then generated for both images. Since the anchor view and positive view are just two different views of the same image, we want to then maximize the agreement between the final predictions using contrastive loss. Where PAWS brings BYOL and SWAB advances to SimClear is by introducing a support set. The support set sample images are taken from the labeled data available and also passed through the encoder to generate labeled representations. When generating a class prediction for the anchor or positive views, PAWS uses the weighted nearest neighbors to measure similarity to the support samples. Since this is fully differentiable, we generate gradients for both views and support samples with respect to the labeled images to update weights. Focusing on the key experiments, we fine-tune PAWS on the dogs dataset for 30 epochs, after pre-training with 1% labeled data on ImageNet for 300 epochs. Each experiment uses a different ratio of labeled to unlabeled images, from 1:1 to a very sparse 1:25. Here we see that the validation accuracy and top one soft nearest neighbors accuracy did drop from 83% to 59% to 81% and 52% respectively, but surprisingly not significantly across all experiments. Analyzing the results using saliency maps show that good representations of dog classes are learned. However, saliency does get more noisy as sparsity increases, with the exception of some classes as seen here with columns 5 and 6. To investigate this exception, confusion matrices help illustrate that the Maltese dog and Bernese mountain dog classes generate high false predictions as sparsity increases. This is possibly because these two classes share many colors and features with other classes. In conclusion, preliminary results show that PAWS does effectively learn fine-grained classes, making it viable for fine-grained classification tasks with sparsely labeled datasets. However, accuracy does diminish as sparsity increases above a 1:5 ratio. Future work includes fine-tuning on other fine-grained datasets to corroborate this conclusion and look to extend to real-world manufacturing applications such as defect detection when datasets aren't readily available, labels are sparse, and classification decisions are fine-grained. Thank you very much.